Is it going to work? Okay, can you all hear me? Yeah?
Yeah.
So I've got the fun job of trying to keep you from coffee, which is already delayed, so I do apologize. I will try to be as quick as possible. I also have the admission that actually there's no machine learning in my talk. So you're all still here, which is good. So yes, I'm James Cumby. I'm from the University of Edinburgh. I'm also from, based in the Department of Chemistry there, but also based in something called CSEC. So this is the Centre for Science at Extreme Conditions. So we've a sort of multidisciplinary centre of physicists, engineers, chemists, you name it, any science. As long as you can justify it as being extreme, then we're happy and interested in talking to you. So I'm going to be talking about ellipsoids as a potential coordination descriptor. So we've seen lots and lots of things. I would argue that actually physical properties, so first and foremost I'm interested in functional materials, and those functions are often described by local structure. So there's a few things that are dependent on the bulk, but often they are dependent on individual bonds. So if we take something like chirality, here we've got two different molecules. For those who don't know, I guess many of you won't, this is thalidomide. So you've got two different enantiomers of thalidomide, one of which is brilliant as an anti-sickness drug, the other one causes birth defects. So just that one change in bond length or bond coordination has a massive effect on the biological response. Other properties, things like electronic and magnetic behavior. So on the right here, we've got an ion complex. Varying temperature causes the bond lengths to change ever so slightly, and you get a spin crossover. So you go from a low spin diamagnetic state to a high spin paramagnetic state, just by changing these local bond lengths. And then going into sort of more condensed matter type arrangements. So here we're looking at negative thermal expansion material. So things like scandium fluoride. So here you've got rigid polyhedra, so in this case octahedra, which are linked via your fluorine, and they bend with temperature. And so if they bend a little bit, that gives you positive thermal expansion, but actually if you rotate these things very rapidly, you can get a net decrease in volume on raising the temperature, which is obviously going to be useful for things in terms, and the example that's always given is dental fillings. If you could have a tooth filling that had zero thermal expansion, you would never have a tooth filling that falls out again, which would be good. And then on to things such as dielectric properties. So this material here is, I'm glad I'm following Carsten, he's given a nice introduction to perovskites. So this is a perovskite material, barium, titanium, oxygen, and this you will all have lots of it in your pockets right now. If you've got a phone in your pocket, if you've got a laptop, they're full of capacitors. Almost all commercial capacitors are based on barium titanate. And it's because it has this huge dielectric response at around room temperature, which makes it very good as a capacitive material. And that is almost entirely due to displacements of your titanium within this central octahedral unit. And so I'm a chemist. I like to think of these things in terms of polyhedra. So in the top right example, we're thinking in terms of a tetrahedron around that carbon. In all of the others, I think in terms of an octahedron. So distortions of how these things are changing with temperature, with pressure, is very important. But rarely are these ideal. So an ideal octahedron, you can all imagine they've got the same bond lengths, all bond angles are 90 degrees. Rarely do you see that in a real material. So this can come from multiple origins, things like electronic effects that I've shown earlier, just actually the connectivity within a structure. Sometimes to fit into this, going back to the graph idea of the previous talk, in order to fit different groups next to each other within a material, you have to distort them slightly. And then other things such as strain, pressure, temperature, they can all deform. So on the right, I'm showing an ideal octahedron. You can elongate it slightly, so that's called a Jahn-Teller distortion, which is important for electronics. You can distort it with an angular sense, or you can just have something there which is a complete mess. And that no longer looks very much like an octahedron. Trying to quantify how octahedral it is a real challenge. And from the point of view of machine learning, you need some way of describing these distortions. So actually, we've covered lots of these in both this workshop and the school beforehand. The simplest one is just look at the bond lengths, look at your bond angles. So there's measures that are used a lot in the literature in terms of the variance of these things, or you can just plug them in as basic numbers. Extending that idea even further is using spherical harmonics, so the SOAP idea. There are other methods based on symmetry that some of you may know. So these are normal modes, so think of vibrations of an octahedron. You can quantify these distortions in terms of those. The problem with all of these is that you get quite a lot of them. So as the number of points on your polyhedron increases, the number of bond lengths and bond angles that are required to describe this goes up hugely. With SOAP, the number of things required goes up even more. So SOAP, you can end up with thousands and thousands of parameters just to describe a fairly trivial distortion. And the same problem is true of symmetry. There's another thing called continuous symmetry or shape analysis. So this is how octahedral is my octahedron. And it's a nice quantitative measure of this, but it has the disadvantage that you have to define a shape pair to. And so in the case of an octahedron, that's very easy. If you had something that had 7 points on the surface, what shape is a 7-point platonic solid? I don't know. You need some reference there. So the method I'm proposing is, I would argue, fairly simple. You take your polyhedron that you're interested in, so your local coordination environment, you find the smallest volume ellipsoid that can fit it. So you take a sphere, start shrinking the principal axes, rotate it round until you find the smallest possible volume that covers all of the points. And that gives you very, very few parameters. So you've gone from 6 bond lengths, however many bond angles, down to 3 radii, shown in yellow here. And those radii define your distortion. So if you've stretched it slightly, one of the radii will be bigger, etc. You can also get an orientation matrix of this relative to the crystal. And then the benefit of this versus something like principal component analysis or linear decomposition is that actually the center of your ellipsoid is not fixed. So the center can move. It doesn't depend on your center of mass. And there are occasions where actually this is really important, barium titanate being one of them. And there's a few things that you can summarize beyond just this. So summary statistics, you could just use the radii in the first place to define your coordination. You can take the mean of them, just gives a measure of how big your coordination environment is. The standard deviation of them is a measure of how distorted it is. And then finally, there's this shape parameter that I've defined that defines how cigar-like or how Smarty-like your ellipsoid is. So if it's 0, this will be a sphere. If it extends up to 1, that's a straight line. If it goes to -1, it's a circle. And this is a nice continuous measure. So from the machine learning point of view, actually, you could go through your structure, calculate these things for all of the atoms you're interested in, and that gives you a vector of description, which is unique to the structure. So you lose a lot of information in the process, but actually it's no worse than something like a PCA, principal component analysis. So I'm going to go on and try and convince you that actually this still represents quite some interesting physics. So previous talk talked about perovskites, talked a lot about cubic perovskites. Actually, they're this interesting family of many, many different distortions. So here I'm showing the perovskite structure without your A cation in the middle. So this is just the BO3 octahedra. And these things in the cubic perovskite, they're all aligned on top of each other in a square array. But actually, you can rotate them. Because they're all corner shared, these rotations propagate throughout space. So you can rotate either clockwise or anti-clockwise. The next layer down you can rotate as well, and again and again. And you can do this across all 3 dimensions. So you end up with all of these different combinations. If you just rotate one way, you get a certain symmetry. If you rotate different axes at the same time, you can go lower in symmetry. In total, there's 15 combinations. And they're all well-defined in this paper. For those who are interested in space symmetry, this is relationships between them. It doesn't really matter for our purpose. The important thing is that actually a lot of perovskites transform with temperature and pressure, and it's a really common occurrence. And the way these are normally defined, as Carsten mentioned before, is in terms of a tilt angle. So you can think of an angle between your metal, your oxygen, and your metal. But actually, as soon as your tilts get more complicated, this angle is no longer well defined. It becomes much harder to rationalize how tilted these things are. So, applying ellipsoids to the process. Here is a really simple example. So this is lanthanum aluminate. These are structural data from neutron diffraction over varying temperatures. And at high temperature, this thing is cubic. So all of the ellipsoids are spherical. As you cool it down, you go to this R3 bar C rhombohedral symmetry. So this is rotating all of your octahedra the same way in all three axes. And that gives you a rhombohedral distortion. And what happens is that you see the radii of your ellipsoids for the lanthanum all distort away from the same value. And actually, the standard deviation shows this nice order parameter behavior. So normally, tilt angle is given as an order parameter for these materials, but actually, ellipsoids works really well as an order parameter as well. So this is the underlying physics is that this is driving the process somehow. And so this has a reduced temperature to the half dependence. The interesting thing is that in most perovskites, we assume that the octahedra are rigid. You've just got these modes that are rotating around each other, but they're completely fixed. In reality, they also distort slightly. So the order of magnitude is very different here. So look at the standard deviation. For the lanthanum, you're looking at 0.08, sorry. Here you're looking at an order of magnitude lower. But when you go through this phase transition, you have to distort your octahedron. And this actually, if you look at the standard deviation of this, obeys an order parameter squared behavior. So this is reduced temperature to the 1. So there's some physics here. This is interesting how one parameter relates to the other during this phase transition. So this is just a really simple example to convince you that it works, but actually there are many more interesting physics to look at. So one example is back to barium titanate. So I've shown before that this has all of these dielectric, ferroelectric phase transitions. Actually, there's a sequence of symmetry reductions as you go down in temperature. And fitting ellipsoids to this material throughout that range, there's some interesting behavior if you look at this shape parameter. So here I'm plotting the shape for both the barium cation and the titanium cation. And hopefully you can all see that as you go through a phase transition, it changes sign. So you're going from a prolate ellipsoid to an oblate ellipsoid, to a prolate, and back and forth as you go through these phase transitions. And there's actually, the rationale behind this is that you've got two competing states. So one is where your coordination environment is stretched. The other is where your coordination environment is squashed. The volume of the two is very similar. So as you cool this material down, there's two competing structures there. The material doesn't really know which way to go. Eventually, it flops one way or the other. Meanwhile, because, as I said before, these ellipsoids define a nice, accurate center of your coordination, you can map out the displacement of the cation. So here I'm plotting the displacement of the titanium away from the center, and that is continuous. So the displacement is the thing that's acting as the order parameter here, and the other things are just a secondary physical effect on top of that. And so this is completely new. No, this physics wasn't understood beforehand. It's related to the symmetries, but it's work's still underway to understand what's going on. And having gone through lots and lots of data in things like the inorganic crystal structure database, looking at more perovskites that also show this sort of behavior, it seems to be that this is dominated by materials that show this off-centering, so second-order Jahn-Teller effect, but it's also promoted by if you have crystal field effects on your large A cation, that promotes this sort of behavior as well. But the important thing that I want to get across is that actually the ellipsoids are finding new physics. So going more into, hopefully, the territory that will be of interest to many of you, this is a data mining approach using this. So in this case, the work started looking at iron oxides, so I extracted all of the materials in the ICSD containing an ion surrounded by oxygen in its coordination shell. And so this is 390 structures, about 500 polyhedra. So it's fairly small data on the big data scale, but it's still got enough to show some interest. And so you can see the different coordination numbers quite readily on the same sort of axes. So here you can compare different coordination numbers. These points up here are the square planar ion. So they're quite rare, there's not many of them, but actually they stand out very readily in this representation. But on the right, I'm just plotting how, so the dashed lines are mathematical limits. So here I'm plotting the standard deviation of your radii against this shape parameter that I defined. There is a mathematical relationship on how distorted you can be while still maintaining that shape. And what we find is that actually most of the materials in the literature lie on these high symmetry, or ideal mathematical limits. So there's not many in the gaps in between. And it shows that materials, if they're distorting, they tend to want to distort as much as possible while still maintaining the structure. So just drilling down a bit further into this, I like octahedra. It's my comfort zone. So I looked at the 6-coordinate ion oxygen, and you can plot out the mean radius against standard deviation and also this off-center displacement. So the top chart is showing, in effect, a measure of your ionic radius. There's nothing new there, but you see that ion 2+ is bigger than ion 3+, as you'd expect. Perhaps more interesting is if you plot the displacement of this ion from the center of the coordination shell for both the ion 3+ and the ion 2+, the ion 2+ does as you'd expect. You have a lot that are not distorted at all, and then this drops off very rapidly to higher distortions. I'm plotting this as a log histogram. So there's an awful lot of structures with no displacement. The interesting one is actually the ion 3+. So here, you've got a lot with no distortion, but then you've got a peak at around 0.15 angstroms. So this is telling you that in the literature, you've got a lot of D5 ion that is displaced from its central position. And so this is going back to a second-order Jahn-Teller idea, that this is well known for D0 systems, so things like titanium 4+, where it will displace, gives rise to a large dielectric effect, and that's because it's got a completely empty d orbitals. Here you've got D5, so it's half-filled, the principle is the same, and this wasn't really known beforehand. So just to wrap up, I want to show that, hopefully I've shown that ellipsoids could be a potential measure of distortion for application to materials. And there's some physics that have come out of this, so the switching by stability in perovskites, this D5 effect for iron 3+, which is actually quite important in terms of multiferroic materials, which are a growing topic, because here you've got a highly magnetic ion coupled with a displacement, which could give rise to a dielectric or ferroelectric effect. And a future aim is to actually use this, applying it to the machine learning side of things. And if anyone's interested, it's all implemented in this PyFace software, which has a terribly contrived acronym and an awful icon that I made. But it's all written in Python. It's readily downloadable. I've tried my best to write documentation for it. I'm always interested to get feedback. It was written for colleagues who didn't like computers, so it has a nice GUI. But I'm guessing most people in this room are happy with command line things, so you can also just use it as a Python package. And with that, I'd like to thank you for your attention.
And we have a time for a couple of questions.
You reckon there is a scope also for using these ellipsoids, which are actually changing their shape as a in a coarse grain model?
Definitely. So they are completely generalizable. As long as you can define some sort of convex hull of points. So to my simple, naive mind, actually just nanoparticle shapes would be a good application of this, because you've got a finite surface, you can wrap an ellipsoid around it. But anything where you can define, in effect, a coordination environment on any length scale. So yes, coarse graining is a definite avenue for this.
You mentioned chirality as one local property that is important. Is that something that would show up in the ellipsoid?
No, is the simple answer to that. So these things, because they are rotationally averaged, you can't capture the chirality. There's some ways that actually you can go to a perturbed ellipsoid. So you can, rather than having a trivariate Gaussian, you could use a skew normal distribution or something. That might be a way around it. It's something I'm working on at the moment.
Thanks.
Questions? If not, let's take a speaker and all speakers in this session.